Again, we're working with the homogeneity property. The homogeneity property deals with power functions. Power functions have the equation y equals c times x to the k power. K is known, so it is an actual number. It's not a variable. And c is a positive value. And again, it is a constant. It is known. X and y are variables. As we read our example, the life expectancy of a star is a power function of its mass. So my first quantity is life expectancy, and it is related to mass. When I'm moving from words to the equation, I use these in order. I'm going to use L for life expectancy, and that is the same as the Y because it came first. I'm going to use M for mass, and mass would be my X value. So then I am able to write a generic equation for this situation. I am told here that my value of my power function is K is negative 2.5. So I know that the life expectancy is some constant times the mass to the negative 2.5 power. What we have in the homogeneity property is that if we multiply the input x by anything, then we have to take that same number, called a factor, to the k power to see the impact over here on y. So we have here that the mass is increased by 43%. So when we're dealing with a percent, we need to change that to a decimal. So 43 divided by 100 is 0.43. And then we need to change this to a factor. So if we want to increase something by 43%, we know that the factor A would be 1 plus the percent. And so that would be for increase because of the plus. And so what we're going to multiply by is 1.43. So this 1 would keep the original amount. This 43 here would give us a 43% increase. So that means that I want to figure out life expectancy. I have this constant. I'm multiplying the mass by 1.43 to have a 43% increase. And then I have this exponent of negative 2.5. So the impact of this multiplication is going to be 1.43 to the negative 2.5 power. And so I'll go to my calculator and type that in. And when I type that in, I get 0.4089. Because this problem is dealing with percents, I'll change that to a percent. So this would be 40.89%. And so when I'm talking in the context here of the homogeneity property, this would be 40.89% as much. So that would say that the life expectancy, because that was our y variable, is 40.89% as much, or as long. What's happening here is that as we increased the mass, our life expectancy actually went down. And that happened because up here we have this negative exponent. And so if we had looked at graphing this, we would have something that would have a negative slope to it. And so it would go down for it. It's not really slope, but a decreasing function. So the next thing that we're going to look at is if the mass is decreased by 14%. So 14% we have to make into a decimal. Now we have the word decreased. Up here we had increased and we added. Decreased, we're going to subtract. So we're going to take 1 minus 0.14. And so we do that math and we have a value of 0.86. So that means in our equation, the life expectancy of the star, there's this constant, will be multiplied by 0.86. And that means that the mass of it would decrease by 14%. 86% of the mass would still be there. and we still have this exponent. So on our calculator, we're going to take our factor, 0.86, to the negative 2.5 power. And when I do that, I get 1.458. And so if I change that to percent, that would actually be 145.8% as much, or as long, because it's a life expectancy. And so this actually represents an increase of 45.8%. This one is acting just like the one up here. When we increased by 43%, we multiplied by the 1.43, and so when we get this answer here of 1.458, that 1 is just the constant original amount, and then the percent here is in the decimal, and we see that it's increasing. And again, this is going opposite of what we expect. It's having an inverse relationship because of the negative. So when the mass goes up, the life expectancy goes down, and here, where the mass went down, then the life expectancy went up.